Okay, let us do another example. I will do 3 examples, okay, simple ones, no complex ones. So, sum, MPI sum. So, we will use it for summing up elements of an array, one array, but this array is dividing into among two processors. So, this is the same array which I used in the last example. So, this array the full data is this full data, okay, this is the full data, but I would divide it into two processors P 0 and P 1, and the numbers are exactly same as what I used in the last example. 0 to 15, oh, there is a problem, 0 to 15 for this what happened, this is all problem, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So, I have copy paste has this problem. Oh, this is also problem. Okay. Anyway, these are some numbers. Okay, some numbers, and I need to do local sum. These numbers are not what I wanted to show, but these are different numbers. But in any case, numbers are there. I want to get the total sum of the full array, but array is divided into processors. Then what should I do? I should compute local sums for each processor and then do the total, right. We have discussed this in the past. We implemented it for multi-threading as well, multi-processing and multi-threading, but let us see what to do in MPI. So, MPI now my matrices are sub matrices, okay, is 4 by 4. The full matrix is 4 rows and 8 columns, but right now each processor is getting 4 by 4. Then I have basically I use the same thing as in the past. It is integer type, okay, this is integer. I could use float as well, but right now it is going to treat as integer, and this is double. So, this will create numbers 0 to 15 and this will create number 0 to 15 into 2 is 30, 0 to 30. So, what should I do for summing? So, this code is running on all the processors. So, each guy sums its own array. So, say local sum equal to np dot sum, easy. Then I want to do the total. So, let us create a variable total which is there in all the processors. I do this total np 0 like. 0 like means it is 0, but like which array variable is like local sum. So, this will make sure that total can be integer, float, depending on what u is. If you right now u is integer, so local sum is integer, so total is also integer, but if for float it will also, this code will work. So, the thing is Python does not require you to declare the type of a variable. You do not need to say u is you do not need to say, but you can say. You do not need to say a variable is integer or float or string, depending on what you put it, it will work. But for MPI it is a good idea, because I am sending big data, good idea to declare like this. Then print local sum. So, this is at this point each processor has computed the local sums and I put it here. Then I want to do the total of all the local sums. Then I use the function reduce, operation is MPI dot sum, and it takes local sum from each processor and puts in total. And who does all this work? Is done by processor 0, which is the master processor, okay, and print total. So, once I do it, so the syntax please do not forget, mp exec minus n to python in array dot py. So, it is running on 2 processors and the name of the file is array dot py. Local sums are 120 and 240 and the total is 360. Please keep in mind that this print is executed by all of them. I should not, I mean this is a slight bug in the code. I should, only master should print it, why should everybody print it? So, master is printing the correct total, and well, both of them printing correct total, but whatever is available with them. So, only master has the correct total, worker 1 has has 0 in total. So, it prints 0. So, I should put here if if rank equal to 0, then print. Okay. So, this is the second example. Third example, I think I have another example or not. Yeah, I have several more examples. So, all to all. Next, we will use all to all. So, I discuss all to all. All to all basically transfers data, fraction of data among all the processes. So, for two processors, we did it for single number in the last time, it was transpose. If you look at your slides, I did for 4 numbers and 4 processes with a matrix, and that became a transpose. So, rows became column, column became rows. By the way, please, you must know how to use this function all to all. Okay. But if I have 2 processes and my data size is big, so my data size is 16 numbers, then what will I do? So, MP all to all will cut the array into pieces equal to number of processes. Right now, there are 2 processes, it will cut into 2 pieces. Had there been 4 processes, it will cut into 4 pieces, it would have been like that. But I have 2 processes only, they will cut into pieces. So, for 2, it is a matrix right now. Okay. So, if I look at the full thing, my matrix will look like this. So, this is this part and this is this part here. So, this guy will remain with itself 0 on 0, this will remain on itself. Okay. So, you do not touch this part and this part, they remain where they are, but these guys are exchanged. Okay. So, instead of a number, I have chunk of numbers and I do exactly same thing like what I did before. Is that clear? So, it is like a transpose, but with not a number, but with a chunk of data. So, I had to transfer these numbers, in fact, they gone there, and these numbers are coming here. So, they have come here, right, 0, 2, 4, 6, 8, 10, 12. These numbers have come here and these numbers have gone here. Okay. These all to all for numbers. So, what you learned for single numbers are to be generalized. Okay. That is the reason why I am giving you this example. For your projects you do not need it, but for FFT this is a very critical function. So, all to all is is very similar to what we did before. You create these arrays and then you send. Receive buffer I create nx by ny. So, receive buffer is okay. It's okay. So, basically this is my receive buffer is same size as before. Okay, and I need to transfer. Well, basically all to all will do all that sending stuff. So, all to all you need to give use. So, it will this function will take both the use and do the send do this task of diagonal transfer, and you will get this. Okay. So, this function is there in Colab and you can run it. Make sure that you are importing, this is installing MPI 4Pi. So, you need to install it for every session, unfortunately. I do not know how to install it for permanently, but you need to install. Once you exit the session, then this library is not installed anymore. Okay. So, pip3 install, and you need to do it on Colab. So, let us compute A star B, sum A and B are vectors. So, I am not doing it for big data. So, my A is a big vector which has 10 power 8 by 2. So, my array was big array 10 power 8 numbers, but now I want to do it in MPI. So, I divide the numbers into two processes. So, A and B both are half the original size. Then I do local sum, it is just like before. So, but I am doing for big array. Okay. And so, I also so this is the time taken. Okay. So, I want you to compute time. Okay. So, now this is the time in seconds. Of course, I need to truncate it like this, but this is time in seconds. Okay. Now, y equal to Ax. Y is A is a matrix, X is a vector and Y is a vector. So, I want to do it in two processes. What should I do? So, this A is a big matrix. It could be 10,000 by 10,000 matrix. So, I have this X equal to Y. So, I want to use two processes for this operation. What do you recommend? Okay, which one? A. Great. So, very good. So, A should be divided into two parts row wise. Why? Because I am going to take X and put it horizontal and multiply. Should I divide X also? No, X should not be divided. Okay. And Y should be divided? Yes, no? Yes, Y should be divided. So, the top half will be computed by processor 0 and bottom half by processor 1. Okay. So, you should, so I mean you understand. So, this is what I multiply element and sum, and the result goes here. Next time I do this, result goes here like this. And well, if I divide like this, then both of these processes can do this work simultaneously and give me result. If you have more than two processors or let us say p processors, then I divide A into p segments row wise. So, that is what is being done here. So, I have my matrix size is 10,000 by 10,000 m by, so I create a new variable m by 2. Okay. Just so, my variable name I would like to use often something which is what it is. Do not use temp or something. Okay. So, many students have this tendency to use I, j, k, temp, temp 1, temp 2, temp 3. So, I had seen a program which is temp 1, temp 2, temp variables were like that, okay, temp 15. Do not use it, you should use what the variable is. So, m by 2 is m by 2, and so then you fill, right now I am putting random numbers, but you fill. So, this program is running on each processor. So, I fill numbers for the segment which I have. So, this is not full A, but it is half of A. So, I am not writing a partial A or something. Okay. A is understood to be the part of the big array, and I put a barrier here. Why do I put a barrier here? These are a big operations. No, I mean these are initialization, and before initialize and I start doing something else, there can be a problem. So, let us put a barrier, so that both these processes have finished their work when it reaches here. So, these two work well, all these three lines should have been executed by both the processors. Then I create a vec 0, which is I am going to put x here, okay, x will be here, but I do not create everywhere, because if I create everywhere, there can be different random numbers, right, x should be same numbers, right. So, I create in one of them, I create in master node. Typically, you ask master node to do the critical things, or something which is to be done once, you let the master do it, keep it as a convention. I create a number, and this, sorry, not number, it is this column, and sorry, this vector is a column vector, and that column vector is to be broadcasted. I use broadcast to send everywhere, and what is the name of the broadcasted vector? Vect. So, vect is same x which was created by root 0 master node, and now everybody has the same x. After that I create a my y vector, okay, which is y column vector. It is m by 2 half, and then I am going to do it for the loop. So, for each row I am going to, for a, I take this x and I multiply. I mean this a colon comma I comma colon, I is a row number, vect all of it, multiply. So, this will achieve this task of multiplying these with these and sum. And where should I go? Where should it go? Ith column, ith entry of y, which is prod I. Okay. That is it. This is the answer. So, well, I mean this is there in every processor. If you want to collect it, this root can gather it. Now, gather can be useful function here. Root can gather and make a big array. So, clear. I mean, so basically whatever you do for sequential, you can use MPI to make it parallel. And one great good idea is to think before you start coding. Do not just jump into it. Okay, I want to start. So, think before, because MPI programs are very difficult to debug. When you print, you do not know who should print, where is data going. So, just design carefully, so that we do not need to debug at all, maybe debug slightly, okay, if it is a problem.